Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight, our journey drifts into one of the strangest and most gently unsettling territories science has ever discovered. We'll be exploring quantum reality, the subtle world beneath space and time, where particles behave like possibilities, distance loses its meaning, and reality itself may be stitched together from information rather than solid things. Before you settle in completely, if you find these calm explorations comforting, you're warmly invited to like this video and subscribe, only if it feels right to you. And if you're still awake enough to do so, you can leave a comment letting me know where in the world you're listening from and what time it is for you right now. It's always a quiet joy to imagine this gentle gathering spread across so many different nights, each of us resting in our own small corner of time. Now, feel free to dim the lights, maybe let a soft fan hum in the background, and allow your body to settle into stillness. There's no need to concentrate too hard. If your mind wanders, that's perfectly fine. These ideas don't demand effort. They simply unfold slowly, like a story told in the dark. And so, with no rush at all, let's begin. You may have noticed something curious about the universe. Most of the time it behaves exactly as you expect. Cups fall when nudged, doors open when pushed. The sun rises, the moon drifts across the night sky, and the ground remains reassuringly solid beneath your feet. Your intuition handles all of this effortlessly. You don't calculate trajectories or equations, you simply know how things work. That intuition feels natural, almost trustworthy. And for the world of everyday experience, it is remarkably reliable. But tonight's story begins with a quiet realization that this intuitive understanding, as helpful as it is, was never designed to explain reality at its deepest level. Your intuition is not a window into the fundamental nature of the universe. It is a survival tool. Long before humans built laboratories or asked abstract questions about existence, our ancestors needed to make fast, practical judgments. Is that shape in the bushes a predator? Will this branch support my weight? If I throw this stone, where will it land? The brains that answered these questions efficiently were the ones that survived. Over countless generations, natural selection tuned human perception to a very specific slice of reality. The warm, slow, medium-sized world where things are solid, separate, and predictable. Atoms were never part of that deal. At the scale of the very small, the universe plays by rules that intuition never had to learn. And when we finally developed the tools to look closely enough, those rules felt not just unfamiliar, but deeply wrong. Not wrong in the sense of incorrect, but wrong in the way a dream feels wrong when you wake up and realize gravity was optional. This is why quantum physics feels dizzying. Not because it is careless or chaotic, but because it asks us to abandon expectations that once kept us alive. In the quantum world, objects do not always have definite positions. Events do not always have single outcomes. Causes and effects do not line up in neat, comforting chains. Instead, reality behaves more like a quiet field of possibilities, waiting to be nudged into something definite. And the first time physicists encountered this behavior, it didn't feel poetic or mysterious. It felt like a mistake. Early experiments at the turn of the 20th century were not designed to overthrow common sense. They were meant to refine existing theories, to polish the details of a universe that already seemed well understood. But nature had other plans. Measurements refused to cooperate. Results contradicted expectations. Light behaved like matter. Matter behaved like waves. And the harder scientists tried to force the universe back into familiar shapes, the more it slipped through their fingers. What made this especially unsettling was that nothing was obviously broken. The experiments worked. The data was clear. The predictions matched what was observed again and again. The only thing that failed was the story we told ourselves about how reality ought to behave. This is an important point, and one worth lingering on gently. Quantum mechanics does not replace reality with confusion. It replaces a simple story with a subtler one. A story where certainty gives way to probability, where outcomes emerge rather than exist in advance, and where observation is not a passive act, but part of the process itself. Imagine standing on a hill at night, looking out over a city filled with lights. From far away, the city seems calm and continuous, a steady glow. But as you move closer, individual streets appear, then buildings, then rooms, and finally, people moving unpredictably within those rooms. The smooth glow was never false. It was just incomplete. In much the same way, the classical world you experience every day is not an illusion. It is an approximation, a beautifully accurate one, at the scale where you live your life. But when you peer deeper, the neat edges dissolve, and the universe reveals a texture that intuition alone cannot grasp. This is where mathematics enters the story, not as an abstract burden, but as a new kind of language. Where intuition fails, patterns remain. Where certainty dissolves, probabilities still obey precise rules. Quantum mechanics does not tell us what must happen. It tells us what can happen and how likely each possibility is to appear. And strangely enough, that turns out to be enough to build computers, explain chemistry, and describe the behavior of stars. But understanding that intellectually is very different from feeling comfortable with it. Our minds crave definite answers. The universe, at small scales, offers something quieter and more patient. It offers a menu of possibilities and waits for interaction to decide which one becomes real. As we drift deeper into this story, you'll see how this simple shift from certainty to possibility echoes everywhere. In experiments where single particles seem to know about multiple paths, in pairs of particles that remain connected across vast distances, in black holes that challenge our ideas about information and loss, and perhaps even in the structure of space and time themselves. For now, it's enough to sit with this gentle discomfort. The universe is not behaving badly. It is behaving exactly as it always has. We are simply learning, slowly and carefully, how to listen. And as your breathing steadies and your thoughts begin to loosen their grip, remember this. Feeling confused by quantum physics is not a failure of understanding. It is a sign that you are brushing up against the edge of what intuition can do. Beyond that edge, a quieter, deeper story is waiting. There is a comforting myth about science that many of us grow up with. It goes something like this. Brilliant minds sit down with clear plans, design elegant experiments, and step by step uncover the secrets of the universe exactly as intended. Reality, however, is usually quieter, messier, and far more accidental. The doorway into quantum reality was not opened by someone trying to make the universe strange. It was opened by people trying very hard to make it behave normally. At the end of the 19th century, physics seemed nearly complete. The motions of planets were understood. Heat, light, electricity, and magnetism had been woven into tidy mathematical frameworks. There was a widespread belief that all that remained was to measure things more precisely, to add decimal places to an already finished picture. And then small, persistent problems began to appear. Light, for example, refused to act consistently. In some experiments, it behaved like a smooth wave, spreading out, bending, and interfering with itself. In others, it arrived in sharp, discrete packets, like tiny pellets striking a surface one by one. Physicists didn't find this poetic or mysterious. They found it annoying. Waves were waves, particles were particles. Mixing the two felt like a bookkeeping error. Even more unsettling were the experiments involving electrons, those tiny carriers of electric charge. When electrons were fired at certain materials, the results looked eerily similar to the behaviour of light waves. Patterns emerged that suggested spreading, overlapping, and interference. Yet every attempt to pin an electron down revealed something solid, localized, unmistakably particle-like. One particularly revealing moment came from an experiment that was never meant to be revolutionary. Equipment malfunctioned. A metal surface was damaged. Instead of discarding the setup, researchers adjusted it and continued. The result was unexpected. Electrons scattered in precise, repeating patterns that could only be explained if they behaved like waves passing through a regular structure. It was not a bold theoretical leap that revealed this behaviour. It was curiosity mixed with patience, and a willingness to listen when nature whispered instead of shouted. What makes this moment so important is not just what was discovered, but how it was discovered. Quantum physics did not emerge from imagination alone. It emerged from stubborn data. Over and over again, experiments insisted on outcomes that no classical picture could explain. And rather than dismissing these results as errors, physicists slowly began to adjust their expectations. This adjustment was deeply uncomfortable. Imagine believing your entire life that shadows must belong to objects, only to discover situations where shadows appear without anything casting them. Or believing that every sound must come from a visible source, only to hear music emerging from empty air. That is roughly how it felt to encounter quantum behaviour for the first time. The universe was not breaking rules. It was revealing that the rules we thought were universal were, in fact, limited. At this point, a subtle but profound shift occurred in how physics approached reality. Instead of asking, "What is this object really doing?" scientists began asking, "What can we say about the outcomes of experiments?" The focus moved away from hidden mechanisms and toward observable patterns. This was not philosophical surrender, it was practical wisdom. Quantum mechanics began to take shape not as a story about tiny billiard balls bouncing in miniature space, but as a framework for predicting what happens when we interact with the world at very small scales. It described tendencies rather than trajectories, likelihoods rather than certainties, and remarkably, it worked. Every prediction it made, no matter how counterintuitive, matched experimental results with astonishing accuracy. The theory did not offer comfort, but it offered reliability. It did not explain reality in the way intuition preferred, but it explained reality as it revealed itself. This is where a crucial misunderstanding often arises. Quantum mechanics is sometimes described as vague, mystical, or imprecise. In truth, it is one of the most precise scientific frameworks ever constructed. Its strangeness lies not in its predictions, but in what those predictions imply about the nature of the world. The equations themselves, when translated gently into words, do not say that anything can happen. They say something much subtler. They describe a structured landscape of possibilities. Some outcomes are more likely than others, some are nearly impossible. And when experiments are repeated many times, the results arrange themselves into beautifully consistent patterns. This is why repetition matters so much in quantum experiments. A single event may look random, almost meaningless. But when the same experiment is performed again and again, order emerges. The universe reveals its preferences, not in individual moments, but in crowds of events, like the slow formation of an image from countless grains of sand. This idea can feel deeply unsatisfying to a mind that wants clear answers. We want to know what will happen next, not just what might happen on average. But nature, at small scales, seems content with offering probabilities and letting outcomes emerge through interaction. It is worth pausing here to notice something gentle and reassuring. Nothing about this behaviour suggests chaos or lack of structure. On the contrary, quantum behaviour follows rules with extraordinary discipline. It is only our expectations, shaped by the macroscopic world, that find those rules unsettling. As researchers gradually accepted this, a new way of thinking took hold. Instead of demanding that reality conform to intuition, intuition would have to stretch. Instead of forcing the universe into familiar stories, scientists would learn to tell new ones, stories where uncertainty was not ignorance, but a fundamental feature. This shift did not happen overnight. It unfolded slowly over decades of debate, disagreement, and refinement. Some resisted it fiercely, others embraced it reluctantly, but the data kept speaking calmly and consistently, and eventually the story adjusted. And so, through accidents, frustrations, and careful listening, physics crossed a quiet threshold. The classical picture of reality, solid and predictable, gave way to something softer and more flexible. A world where particles could spread like whispers, where outcomes were born from probabilities, and where certainty was no longer guaranteed in advance. As you rest with this idea, there is no need to resolve it. Quantum reality does not demand immediate understanding. It invites patience. It invites us to slow down, to accept that the universe may not owe us simple explanations, and that clarity sometimes arrives only after we release the need for it. In the next gentle turn of this story, we will look more closely at one particular experiment, simple in design but endlessly revealing. An experiment that takes all of these quiet hints and brings them together in a single, unforgettable pattern. But for now, it is enough to remember this. The quantum world was not discovered by chasing strangeness. It was discovered by paying attention when reality refused to behave as expected. There is a reason this experiment returns again and again in the story of quantum physics. It is simple enough to describe without advanced equipment, yet deep enough to unsettle everything we think we know about how the world works. It does not shout. It does not rely on exotic machinery. It simply asks a quiet question and waits patiently for the universe to answer. Imagine a solid wall with two narrow openings cut into it, like two closely spaced doorways. Behind the wall sits a screen that records where arriving particles land. Now imagine standing on the other side of the wall, sending tiny objects toward those openings one at a time. If those objects are ordinary particles like grains of sand or tiny beads, the result is exactly what your intuition expects. Each particle chooses one doorway or the other. Over time, two gentle piles form on the screen behind the wall, lined up neatly with the two openings. Nothing surprising happens. The world behaves sensibly. Now imagine replacing those beads with something smaller, much smaller. Electrons, for example, or particles of light, which we often call photons. We send them toward the same two openings, still one at a time, still with great care. And at first, nothing seems unusual. Each arrival leaves a single dot on the screen, as if a tiny particle struck it. But as time passes, something remarkable begins to appear. The dots do not form two simple piles. Instead, they slowly arrange themselves into a delicate pattern of bright and dark bands. Stripes of higher and lower density emerge, spreading across the screen like ripples frozen in place. This pattern is not random. It is structured, and it is exactly the pattern you would expect if waves, not particles, were passing through both openings at once and interfering with themselves. This is the moment where intuition quietly gives up. Waves make sense when we think about water or sound. They spread out, they overlap. Where two wave crests meet, the effect is stronger. Where a crest meets a trough, they cancel. This interplay creates bands of reinforcement and silence, brightness and darkness. But particles, at least as we imagine them, do not do this. They go through one opening or the other. They do not interfere with paths they did not take. And yet the pattern insists. What makes this even more unsettling is that the particles are sent one at a time. There is no crowd, no swarm. Each electron, each photon travels alone. There's nothing else nearby to interfere with it. And still, over many repetitions, the same wave-like pattern emerges. It's as if each particle is somehow aware of both openings, as if it explores all available paths before deciding where to land. Not consciously, of course, but in a way that defies the idea of a single, well-defined trajectory. At this point, a natural thought arises. Perhaps the particles are interacting with each other in subtle ways we have not accounted for. But this explanation collapses under careful testing. The particles are isolated. The experiment is repeated under conditions so controlled that no hidden communication is possible, and the pattern remains. Another thought follows. Perhaps each particle really does choose one path, but we simply do not know which one. Maybe the interference pattern is a statistical illusion born of ignorance. But when physicists tried to formalize this idea, it led to contradictions. The mathematics refused to cooperate. The pattern was not compatible with any picture where particles secretly picked one path in advance. The universe once again declined to fit into a comfortable story. To make matters more curious, if we modify the experiment slightly, the pattern changes. If we place a detector near the openings to determine which path each particle takes, the interference pattern disappears. The screen now shows two simple piles, just as intuition predicted in the first place. The act of checking removes the wave-like behaviour. This is not because the detector physically pushes the particle around. The effect remains even when the interaction is made as gentle as possible. It is the availability of path information that matters. When the experiment is set up in a way that allows the path to be known, even in principle, the universe behaves differently. This is a subtle point, and one that deserves a soft explanation. It is not that observation magically changes reality, it is that interaction does. Measuring is not passive, it is a physical process. And when a particle becomes entangled with its surroundings in a way that marks its path, the delicate structure of overlapping possibilities is disrupted. The wave-like pattern is not destroyed by force, it fades because the conditions that allowed it no longer exist. At this stage, physicists introduced a new way of describing what was happening. Instead of imagining particles as tiny objects following precise routes, they described them using a mathematical object that encodes all possible paths at once. This description does not say where the particle is. It describes where the particle could be and how strongly each possibility contributes to the final outcome. When translated into gentle language, this idea says something like this. Before a particle is detected, its behavior is spread across a landscape of possibilities. It does not commit to a single story. Only when it interacts in a way that forces a choice does one outcome become real for us. The interference pattern is the fingerprint of this landscape. Each bright band on the screen marks places where possibilities reinforce one another. Each dark band marks places where possibilities cancel out. The final image is not drawn by particles deciding where to go. It is drawn by probabilities shaping themselves over time. This is why the double-slit experiment is often described as the heart of quantum mechanics. It contains, in a single setup, nearly all of the theory's most unsettling implications. Particles that behave like waves. Outcomes that depend on what can be known. a reality that refuses to exist in a fully definite way until interaction demands it. And yet, despite how strange this sounds, the experiment is not ambiguous. It is repeatable. It is precise. It has been performed countless times with electrons, atoms, and even complex molecules. Each time the same pattern emerges under the same conditions. The universe is not improvising. It is following rules. Rules that simply do not resemble the ones our intuition learned to expect. As you sit with this image, two openings in a wall and a pattern slowly forming in the dark, there is no need to resolve its meaning just yet. For now, it is enough to notice how gently the universe is challenging us, not with explosions or paradoxes, but with quiet consistency. One particle, two paths, and a result that tells us something profound. Reality, at its deepest level, may not be a collection of definite things moving through space, but a process in which possibilities come together, interfere, and finally settle into the outcomes we observe. And as this idea settles into your thoughts, softly and without urgency, we can let it rest there for a moment. Because the next question that naturally arises is even quieter and even more unsettling. If the particle does not choose a path until it is measured, what exactly changes at that moment? And what does that say about the nature of reality itself? At first glance, the interference pattern from the double-slit experiment feels like a collective phenomenon. Ripples suggest crowds, bands suggest cooperation. It is tempting to imagine many particles whispering to one another, coordinating their landings like dancers rehearsing a routine. But this intuition, comforting as it is, does not survive careful testing. So physicists did something quietly radical. They slowed everything down. Instead of sending a steady stream of particles toward the two openings, they sent them one at a time. Not metaphorically one at a time, but truly alone. A single electron released, a long pause, another single electron, another pause. Enough time between each arrival that no particle could possibly interact with the next. The screen behind the wall began almost empty. A lone dot appeared where the first particle landed, then another dot somewhere else. At this stage, nothing looked unusual, a handful of random marks scattered without pattern. If the experiment had stopped there, no one would have been surprised. But it did not stop. As minutes turned into hours, the dots continued to appear. Slowly, almost imperceptibly, a structure began to form. Regions of higher density emerged. Other regions remained oddly sparse, and eventually, unmistakably, the familiar pattern appeared again. The same bright and dark bands, the same signature of wave-like interference. This is the moment where many people feel a quiet vertigo. Each particle arrived alone, each left a single dot, and yet the final image looked as though every particle had known about all the others that came before it. It was as if the pattern existed in advance, patiently waiting to be filled in dot by dot. There is no known way for a particle to remember where previous particles landed. There is no mechanism by which it could receive instructions from the past, and yet the collective result behaved as though each arrival was guided by an invisible template. To make sense of this, physicists had to let go of a deeply ingrained idea, the idea that each particle follows a single, definite path through space, like a pebble thrown through the air. The experiment simply refused to support that picture. Instead, a different image began to take shape. Before a particle is detected, it does not travel along one route or the other. It does not secretly choose a doorway and keep its choice hidden. Rather, its behavior is described by a spread of possibilities that includes all allowed paths at once, not as physical trails, but as contributions to what might happen. This description can feel abstract, so it helps to soften it with an image. Imagine walking through a forest at dusk. There are many possible paths ahead of you, branching and weaving. Before you take a step, none of them is your path yet. They are simply options, each with its own likelihood, shaped by the terrain. Once you choose and begin walking, one path becomes real in your experience. The others fade, not because they vanished, but because they were never taken. In the quantum world, something similar happens, but with an important difference. The particle does not choose a path in advance. The choice emerges only when interaction forces it to. Until then, the landscape of possibilities remains active, overlapping, and capable of interfering with itself. This is why the interference pattern builds up even when particles arrive one by one. Each arrival is guided not by memory or communication, but by the same underlying structure of possibilities. The dots are not random. They're shaped by a quiet probability landscape that remains consistent from one particle to the next. Another way to picture this is to think of a long exposure photograph of the night sky. A single star appears as a point of light, but when the camera is left open long enough, patterns emerge, trails form. The structure of motion becomes visible, not because any one moment contained it all, but because repetition revealed it. The interference pattern is like that photograph. Each particle contributes a single point. The pattern emerges only through patience. This understanding also explains why changing the setup of the experiment changes the outcome. When information about the particle's path becomes available, even in principle, the landscape of possibilities changes. The overlapping options that once interfered with one another no longer coexist in the same way. The structure that guided the pattern dissolves, and the dots rearrange themselves accordingly. Nothing mystical needs to be added to explain this. No conscious observer is required. No act of human attention reaches into the experiment to alter reality. What matters is interaction. When the particle becomes entangled with its environment in a way that distinguishes paths, the delicate balance of possibilities is disrupted. The universe responds not to curiosity, but to physical conditions. At this point, it becomes tempting to ask a very human question. Where is the particle before it is detected? Is it everywhere? Is it nowhere? Is it split into pieces? These questions, while natural, are shaped by classical thinking. They assume that being must resemble location. Quantum mechanics offers a quieter answer. Before detection, the particle is not somewhere in the ordinary sense. It is described by what it can do, not where it is. It exists as potential behavior rather than definite position. This is difficult to accept, not because it is illogical, but because it asks us to redefine what we mean by existence. We are accustomed to thinking that things exist first, and then do things. In the quantum world, this order is often reversed. Behavior comes first. Definiteness follows. It is important to notice that none of this undermines the reliability of the theory. On the contrary, it strengthens it. The same rules that govern a single particle arriving alone also govern millions arriving together. The same probability landscape guides each event. The universe is consistent, even if its consistency takes an unfamiliar form. As this idea settles, something subtle begins to shift. The world feels less like a collection of objects moving through space, and more like a process unfolding through interactions. Space becomes a stage where possibilities play out, not a container filled with tiny marbles following predetermined tracks. And this shift prepares us for the next question, one that has lingered quietly in the background since the first dot appeared on the screen. If a particle's behavior remains spread across possibilities until interaction forces a result, what exactly happens at the moment of detection? What turns a landscape of options into a single outcome? The answer to that question is not simple. In fact, it remains one of the deepest open puzzles in physics, and it leads us directly into the heart of what is known as the measurement problem. For now, let the image rest gently in your mind. a dark room. A quiet apparatus, a screen slowly filling with points of light. No rush, no drama, just patience revealing structure. One by one, the universe leaves its marks, and in those marks, a deeper story begins to take shape. By now, the image has settled in gently. A screen in the dark, a single particle arriving, a dot appearing, and over time, a pattern slowly revealing itself, not through intention or memory, but through repetition. At this point in the story, many people begin to sense that something important is missing. If particles are not choosing paths, and if the pattern is not built from communication between arrivals, then what is guiding where each dot appears? The answer physics offers is surprisingly calm. It is not a force pushing particles into place. It is not a hidden mechanism ticking away behind the scenes. It is description, a way of speaking about the world that replaces certainty with likelihood and trajectories with tendencies. This description is often called a wave, but not the kind you imagine rolling across water or vibrating through air. This wave is not made of anything physical. It does not slosh or ripple in space. Instead, it lives in mathematics, quietly encoding how strongly different possibilities contribute to what may happen next. To make this idea feel less abstract, imagine standing on a hillside covered in mist. The ground beneath you slopes gently in some directions and steeply in others. You cannot see far, but you can sense where it would be easier to walk and where it would be difficult. This landscape does not force you to move in any particular direction. It simply shapes the chances of where you might go. The probability wave plays a similar role. It does not tell a particle where it must land. It shapes the likelihood of different outcomes. Some locations are favoured, others are unlikely, and when the experiment is repeated many times, those preferences become visible as patterns. This is why the interference bands appear. Where possibilities reinforce one another, the landscape rises and dots appear more frequently. Where possibilities cancel, the landscape dips and dots become rare. Nothing is pushed, nothing is decided in advance. The structure emerges from the quiet arithmetic of possibility. It is here that mathematics enters the story, not as a barrier, but as a translator. The equations of quantum mechanics do not describe particles moving along precise paths. They describe how the probability wave evolves over time. Given a particular setup, 2 openings in a wall, a source of particles, a screen to record arrivals. The mathematics tells us how the landscape of possibilities shifts and reshapes itself. There's no need to write symbols or formulas to understand the essence of this. What matters is the relationship. The probability of an outcome is related to the strength of the possibility at that location. Where the possibility is strong, outcomes appear often. Where it is weak, they appear rarely. And when possibilities overlap, they combine in ways that can either enhance or suppress the final result. This idea can feel unsettling because it runs counter to how we usually think about causes. We're used to imagining a chain of events, one thing leading neatly to the next. Quantum mechanics asks us to think instead in terms of contributions. Many potential stories coexist, and the final outcome reflects their combined influence. Importantly, this does not mean the universe is vague. The mathematics that governs these contributions is exact. Given the same conditions, it will always produce the same probability landscape. And when experiments are repeated carefully, the results line up with those predictions to extraordinary precision. The apparent randomness lies not in the rules, but in the outcomes of individual events. This distinction is subtle, but it is crucial. A single dot on the screen tells us very little. It could have appeared almost anywhere, but 1,000 dots tell a clear story. 10,000 dots reveal the structure unmistakably. Order does not vanish in the quantum world. It simply hides in crowds. This is why quantum mechanics places such emphasis on statistics. It is not because nature is careless, but because nature speaks most clearly through repetition. The universe is consistent, but it expresses that consistency in patterns rather than promises. At this point, a common question arises. If the probability wave is not physical, what is it? Is it just a mathematical trick, or does it represent something real? Different interpretations answer this question in different ways, and we will explore those paths gently later. For now, it is enough to notice that the probability wave does real work. It predicts outcomes, it shapes experiments, it leaves fingerprints on screens and detectors. Whether it is a thing or a description, it cannot be dismissed. Another important point is often missed in popular discussions. The probability wave does not describe our ignorance. It is not a statement about what we do not know. It is a statement about what is possible. Even with complete information about the experiment, the outcomes remain distributed. The uncertainty is not in us. It is built into the structure of the theory. This is perhaps the deepest shift of all. In classical physics, uncertainty comes from lack of knowledge. If we knew everything, we could predict everything. In quantum physics, even perfect knowledge leads only to probabilities. The universe itself seems content to leave room for chance. And yet this chance is not arbitrary. It is constrained, shaped, and remarkably stable. The same experiments performed in different laboratories, on different continents, at different times, produce the same patterns. The landscape of possibilities is not personal, it belongs to the world. As you let this idea settle, it may begin to feel less threatening and more curious. Reality at small scales is not a rigid script. It is a quiet improvisation within strict boundaries. Freedom and structure coexist, woven together by mathematics. This way of thinking also explains why quantum mechanics has been so successful. Chemistry, electronics, lasers, and modern technology all rely on these probability landscapes behaving exactly as predicted. Engineers do not need particles to have definite paths. They need reliable patterns, and the quantum world delivers those with remarkable fidelity. Still, something unresolved remains. If the probability wave guides outcomes, what happens to it when a particle is detected? Does it vanish? Does it change? Does it become something else entirely? This question brings us to a gentle but profound tension at the heart of quantum mechanics. A tension between smooth, continuous evolution and sudden, definite results. Between a world described by overlapping possibilities and a world experienced as singular events. That tension is known as the measurement problem. For now, let the image of the probability landscape rest quietly in your mind. A soft terrain of possibility, shaping outcomes without forcing them. A language that speaks in likelihoods rather than certainties. A way of understanding reality that asks us not to predict every step, but to listen for patterns. And as your thoughts begin to slow, you may notice something subtle. The universe, as described by this gentle mathematics, feels less like a machine and more like a process. Not a clockwork ticking away, but a quiet unfolding, guided by rules that are precise, yet patient. In the next part of our journey, we will turn toward the moment where possibility gives way to experience. The moment when a particle arrives, a dot appears, and the universe seems to make a choice. By the time we reach this point in the story, something subtle has already changed. The universe no longer feels like a place where objects simply move from one location to another. It feels more like a quiet conversation between possibilities, a conversation that continues even when no one is listening. To understand the puzzle at the heart of the measurement problem, We need to pause gently and listen to how the quantum world speaks before it gives us an answer. In everyday life, we're surrounded by clear alternatives. A light is either on or off. A door is either open or closed. A coin lands either heads or tails. Our experience is built from clean divisions, and our language reflects that. We are fluent in awe. But the quantum world begins somewhere else entirely. At very small scales, reality does not speak in awe. It speaks in and. This does not mean confusion. It does not mean indecision. It means coexistence. When physicists say that a quantum system exists in a superposition, they're not suggesting that it is blurry, unfinished, or broken. They're saying something much calmer and much stranger. Multiple possibilities are present at the same time, layered together, each contributing to what may eventually happen. A helpful way to picture this is through soft shadows cast by a single object in overlapping light. In the glow of one lamp, the shadow is sharp and definite. But add a second lamp and the shadow spreads. Add a third and it becomes a gentle gradient. The object has not split. The shadows are not mistakes. They're all valid expressions of the same situation under different lighting. Quantum superposition works in a similar way. A particle does not sit in one state or another. It occupies a combination of states, each weighted by how strongly it can influence the outcome. These possibilities overlap, interfere, and coexist without cancelling one another out. This is not a metaphor invented to make the math feel nicer. It is a direct reflection of what experiments reveal. In the double-slit experiment, before a particle is detected, it behaves as if it has access to more than one path at once. In probability landscapes, before an outcome appears, multiple futures remain active. In every carefully controlled test, the same pattern emerges. The universe keeps its options open. What makes this difficult is not the idea itself, but how deeply it conflicts with our expectations about reality. We're used to thinking that things must choose what they are before they can act. Quantum physics quietly suggests the opposite. Behavior comes first, definiteness comes later. In this and world, a particle can be associated with multiple positions, multiple energies, or multiple states of motion at the same time, not because it is indecisive, but because the conditions that would force a single answer have not yet arrived. This does not mean that anything goes. The possibilities are not infinite or chaotic. They are carefully structured. Some are strong, others are weak, some reinforce one another, others cancel out. The rules governing this structure are precise, reliable, and astonishingly successful. The and is disciplined. Another way to soften this idea is to think about music. When several notes are played together, you do not hear confusion. You hear a chord. Each note remains distinct, yet the sound that reaches you is a blend. The chord is not one note or another. It is all of them together, coexisting. Quantum states are like that chord, multiple notes of possibility sounding at once, forming a whole that cannot be reduced to a single part without changing it. This is why quantum reality does not choose an outcome on its own. There is no internal moment of decision ticking away behind the scenes. As long as the system remains isolated enough to preserve its overlapping possibilities, the and continues. Choice enters only when interaction enters. And this is where things begin to feel especially strange. Because if reality at small scales naturally exists as a layered combination of possibilities, then the world we experience, the world of definite outcomes and clear alternatives, is not the default state of things. It is a special case, a result of something happening to those possibilities. This realization can feel unsettling, but it can also feel strangely gentle. The universe is not constantly making decisions. It is not rushing toward outcomes. It is content to remain open. to let possibilities coexist until conditions demand otherwise. Importantly, none of this requires awareness or intention. The quantum world does not wait for a human mind to notice it. The "and" is not sustained by observation in the everyday sense. It is sustained by isolation. As long as a system is not forced into a situation where its possibilities must become distinguishable, they remain free to overlap. This helps clear up a common misunderstanding. When people hear that quantum systems behave differently when measured, it can sound as though human attention is doing something magical. That is not what is happening. Measurement is not about watching. It is about interacting in a way that leaves a record. Before that record exists, the universe allows ambiguity. And ambiguity in this context is not a flaw, it is a feature. The unworld is not less real than the all-world we experience. It is deeper. It is the layer from which our familiar reality emerges. The certainty we live with is built on top of a foundation that remains flexible, probabilistic, and open. As you let this idea rest, it may help to notice how often something similar happens in everyday life, just on a quieter level. Before a decision is made, several futures are alive in your mind. Before a story ends, multiple endings feel possible. Before sleep arrives, thoughts drift without settling. Quantum physics suggests that reality itself behaves a bit like that, lingering in possibility before committing to experience. This does not mean that the universe is uncertain in a careless way. It means that certainty is not fundamental. It is something that happens. And this sets the stage for the central tension we're about to explore. If the world at its core speaks in "and," why do we, without exception, experience awe? Why do we never see overlapping shadows of reality in our daily lives? Why does every moment arrive as a single outcome, clean and definite? The transition from "and" to "or" is not just a technical detail. It is one of the deepest questions physics has ever faced. It asks where the line is drawn between possibility and experience, between what can happen and what does happen. For now, there is no need to answer that question. It is enough to notice it gently, like a thought passing through the mind as sleep approaches. The universe, it seems, is comfortable holding many possibilities at once. The mystery is not that it does this. The mystery is how it ever stops. By now, the world of "and" has had time to settle into the background of your thoughts, a place where possibilities overlap, where outcomes are not chosen in advance, and where reality remains open as long as it can. And yet, when you look around your own life, none of this openness seems to appear. You never see a cup both on the table and on the floor. You never hear a sound that is both loud and quiet at once. Every moment arrives as a single, definite experience. The universe may speak in "and," but we live entirely in awe. Understanding why this happens is the heart of the measurement problem, and it begins with a quiet shift in perspective. Measurement is often imagined as an act of looking, of checking, of becoming aware. But in quantum physics, measurement has very little to do with awareness at all. Measurement is interaction. Whenever a quantum system meets something large enough, complex enough, or noisy enough to leave a lasting trace, the delicate coexistence of possibilities begins to change. The overlapping options that once spoke together start to separate. Not suddenly, not dramatically, but steadily and irreversibly. To soften this idea, imagine writing a message on the surface of still water. As long as the water remains calm, the shapes can overlap, distort, and blend. But once the water freezes, every ripple is locked in place. The motion that once allowed fluid combinations gives way to a single, fixed pattern. In quantum systems, interaction plays a role similar to freezing. When a particle interacts with its surroundings in a way that records information about what happened, the landscape of overlapping possibilities loses its ability to interfere with itself. The "and" does not disappear, it becomes inaccessible. This is why we never see superpositions in daily life. It is not because they do not exist. It is because the world around us is constantly interacting, constantly recording, constantly leaving traces. Air molecules collide, light scatters, surfaces vibrate, heat flows. Every one of these interactions quietly forces possibilities to separate. By the time anything reaches our senses, the outcome has already settled into awe. This process does not require a human observer. A rock does not need to be watched to be solid. A detector does not need to be understood to record a signal. The universe does not wait for consciousness to step in. It responds to physical conditions. This point cannot be overstated because it is one of the most persistent misunderstandings in discussions of quantum physics. Reality does not change because someone is paying attention. It changes because systems interact in ways that leave marks behind. When a measurement device registers a result, it is not collapsing reality with awareness. It is becoming entangled with the system it measures. Information spreads outward into wires, screens, memory, and eventually the wider environment. Once that information is dispersed, the overlapping possibilities can no longer recombine. The universe moves on. From our perspective, this process feels instantaneous. One moment there is uncertainty, the next there is a result. But underneath that simplicity lies a gradual loss of coherence, a quiet fading of the ability for possibilities to overlap meaningfully. This is why the classical world feels so stable, not because it is fundamentally different, but because it is constantly bathed in interaction. The all-world is not imposed on reality. It emerges naturally from the sheer complexity of everything touching everything else. There is something deeply comforting in this realization. It means we do not have to imagine reality as fragile, constantly on the verge of dissolving into ambiguity. On the contrary, the definiteness of our experience is robust. It is reinforced every moment by the environment we live in. At the same time, there is something humbling about it. The clarity we experience is not the whole story. It is the visible surface of a deeper process that remains hidden beneath layers of interaction. This brings us to the central question that has quietly hovered in the background since the first interference pattern appeared on a screen. When a measurement occurs, does something fundamental happen to reality itself? Or is the appearance of a single outcome simply how reality looks from inside a world saturated with interaction? Some physicists have suggested that there is a genuine physical collapse, that at a certain moment possibilities truly vanish, leaving only one outcome behind. Others argue that nothing special happens at all. The universe continues its smooth evolution, and the appearance of collapse is a consequence of how information spreads and becomes inaccessible. What is striking is that both perspectives lead to the same predictions. Every experiment, every test, every careful measurement agrees with the theory's calculations. The disagreement is not about what we observe, but about how we interpret what observation means. This is why the measurement problem is not a failure of quantum mechanics. It is a mirror held up to our assumptions about reality. It forces us to ask whether definiteness is fundamental, or whether it is something that emerges only when systems become entangled with the world around them. And this question, once asked, does not stay contained. It spills outward, touching everything from the nature of time to the structure of space itself. For now, it is enough to notice how gently the universe guides us toward awe. Not through command, not through awareness, but through connection, through interaction, through the quiet accumulation of information that cannot be undone. As you rest with this idea, you might notice how similar it feels to falling asleep. Thoughts that once overlapped freely begin to settle. Possibilities narrow. One state replaces many. Not because the others were wrong, but because the conditions have changed. Sleep does not destroy wakefulness. It makes it inaccessible. In the same way, the quantum world does not destroy its and. It simply moves into a regime where or is all we can experience. This understanding does not solve the mystery, but it softens it. It turns the measurement problem from a sharp paradox into a gentle question about perspective, interaction, and emergence. And with that question resting quietly in the background, we're ready to take a step back and look at how different physicists have learned to live with this strangeness. Not by resolving it, but by choosing ways to think about it that allow progress to continue. For now, let the certainty of your surroundings feel reassuring, the chair beneath you, the steady rhythm of your breath, the calm definiteness of the moment. All of it resting on a deeper layer of possibility that never quite disappears, even as experience moves on. After encountering the measurement problem, many people expect physics to offer a clear resolution, a definitive statement about what truly happens when possibility becomes experience. But instead of a verdict, history offers something quieter, a pause, a practical compromise. What came to be known as the Copenhagen interpretation was not a triumphant answer to deep questions. It was a truce. To understand why this truce mattered, it helps to remember the atmosphere in which quantum mechanics was developing. Experiments were producing astonishingly accurate results, but the stories needed to explain those results felt increasingly fragile. Every attempt to picture what was really happening seemed to introduce contradictions or paradoxes. The more detail one tried to add, the less stable the picture became. So some physicists chose a different path. Rather than asking what quantum systems are doing when no one looks, they focused on what can be said about measurements and outcomes. The theory, they argued, is a tool. Its purpose is to predict the results of experiments. If it does that flawlessly, perhaps it does not need to say more. This attitude is often summarized by a phrase that sounds almost dismissive. Don't ask what it means, just calculate. But behind this blunt expression lies something more subtle. It is an acknowledgement of limits, a recognition that demanding a classical picture of quantum reality might be asking the wrong question. In the Copenhagen view, the probability wave is not a physical object moving through space. It is a mathematical description of our knowledge, or more precisely, of what can be predicted about future measurements. Before a measurement occurs, the theory provides probabilities. After a measurement, those probabilities are updated to reflect what has been observed. The so-called collapse is not described as a physical event unfolding in space and time. It is a change in description, a shift from one set of predictions to another, prompted by new information. This approach can feel unsatisfying if you're looking for a story about what reality is doing behind the scenes, but it is remarkably effective if your goal is to make accurate predictions. And for much of the 20th century, that effectiveness mattered more than philosophical comfort. The Copenhagen truce allowed physics to move forward. With it, scientists built models of atoms, explained chemical bonds, developed semiconductors, lasers, and the foundations of modern electronics. The theory worked so well that questioning its meaning began to feel almost indulgent. Why risk breaking something that functions perfectly? At the same time, the interpretation carries a quiet humility. It does not claim to reveal ultimate truth. It simply refrains from speculation beyond what experiments can confirm. Reality, in this view, is not denied. It is bracketed, placed gently to the side. There is something sleep-friendly about this stance. It does not force conclusions. It does not escalate paradoxes. It accepts ambiguity as a cost of progress and chooses to live with it. Yet this very restraint is also its greatest source of tension. By refusing to say what happens between measurements, the Copenhagen approach leaves a gap, a space where curiosity naturally gathers. For some, this gap is acceptable. For others, it feels like an unfinished sentence. Another subtle feature of this interpretation is the way it draws a line between the quantum world and the classical one. Quantum rules apply to microscopic systems. Classical descriptions apply to measuring devices and everyday objects. Where exactly that line lies is left deliberately vague. This vagueness is not an oversight. It is part of the truce. The boundary is wherever it needs to be for the theory to function. Critics have long pointed out that this feels unsatisfying. If everything is ultimately made of quantum constituents, why should classical behavior be fundamental anywhere? Shouldn't the rules apply universally? Supporters reply that demanding such universality may be premature. The classical world, after all, is not an illusion. It is the world we interact with. It is the language of instruments, records, and results. Treating it as a given is not a philosophical failure, but a practical necessity. In this way, the Copenhagen interpretation reflects a broader attitude toward knowledge. It values what can be said clearly over what can be imagined deeply. It prefers reliable prediction to speculative explanation. It keeps its promises narrow and fulfills them completely. There is a quiet wisdom in that. But there is also a quiet cost. By stepping back from questions of underlying reality, the Copenhagen approach leaves open the possibility that something important remains unspoken, that the theory, as powerful as it is, may be incomplete as a description of what the world is actually doing. This tension has never fully disappeared. It has simply been set aside when more urgent work demanded attention. As you rest with this idea, it may help to think of the Copenhagen truce as a well-lit room with a closed door. Inside the room, everything works. The furniture is solid. The tools are reliable. Outside the door, there may be something vast and uncertain. But as long as the work can be done inside, opening the door is optional. For decades, physics thrived in that room. Only later, as experiments became more refined and questions more precise, did some physicists begin to feel that the closed door itself was part of the puzzle. That understanding quantum mechanics fully might require stepping beyond the truce and asking again what reality might look like when described without compromise. For now, however, the Copenhagen interpretation stands as a reminder that progress does not always come from resolving mysteries. Sometimes it comes from learning how to live alongside them. The universe, it seems, allows this. It offers us a theory that works, even if it withholds a story that satisfies every curiosity. And as your thoughts drift, that may feel like a fitting place to pause, not with answers, but with a gentle acceptance of limits. A recognition that knowing how to calculate can sometimes be enough to let the mind rest. From here, the path will slowly open again. Other interpretations will step forward, each offering a different way to make peace with the same strange facts. Some will expand reality, some will refine it, some will question the completeness of the picture itself. But for this moment, the truce holds, and within it, the quiet success of quantum mechanics continues, steady and reliable, even as deeper questions wait patiently in the background. Once the Copenhagen truce had settled in, physics moved forward with remarkable confidence. The calculations worked, the predictions matched reality, technology flourished, and yet for some physicists, a quiet discomfort remained. Not with the results, but with the silence surrounding what those results meant. If the mathematics of quantum mechanics is taken at face value, without adding extra rules or exceptions, it tells a very particular story. a story so strange that many hesitate to repeat it out loud. This story is often called the many worlds interpretation. At its heart, many worlds begins with a simple decision. It refuses to add a special moment where possibilities suddenly collapse into a single outcome. Instead, it takes the equation seriously, all the way through. According to those equations, the probability wave evolves smoothly and continuously. It never jumps, it never breaks, it never chooses. If that is true, then the world never truly moves from and to or. Instead, every possible outcome continues to exist. To soften this idea, imagine reading a book that contains every possible ending to a story. At the beginning, all endings are equally available. As you turn the pages, the narrative begins to narrow. Characters make choices, paths diverge. By the time you reach the end, you're following one specific storyline. Now imagine that instead of discarding the other endings, the book quietly keeps them all. Every branch continues, each fully formed, each internally consistent, each unaware of the others. This is the picture many worlds offers. When a measurement occurs, the universe does not collapse into one outcome, it branches. One branch contains one result. Another branch contains a different result. Both are real. Both continue forward, carrying their own histories. From the inside, each branch feels unique and complete. Observers within it experience a single outcome, an or. But globally, the universe remains an and. This idea can feel overwhelming at first. It seems to multiply reality beyond necessity. Countless versions of the universe endlessly branching with every interaction. For many people, this feels extravagant, even absurd. And yet, proponents of many worlds argue that it is, in a strange way, the simplest option. It removes the need for collapse. It removes the need to explain when or how possibilities vanish. It keeps the mathematics clean and uninterrupted. Nothing special needs to happen at measurement. The equations do exactly what they always do. The cost of this simplicity is not mathematical, it is emotional. Accepting many worlds means accepting that reality is far larger than anything we can experience. That every outcome that can happen does happen somewhere. That there are versions of events that unfold differently, even when we are certain of our own path. This challenges deeply held intuitions about uniqueness and identity. It raises questions that are not easily settled. If there are many versions of you, what does it mean to be you? If every choice leads to branching, what gives weight to decision at all? Many Worlds does not answer these questions. It simply insists that the universe does not owe us comfort. It is important to notice something subtle here. Many Worlds is not science fiction. It does not rely on speculation beyond the theory. It does not add new mechanisms or hidden variables. It arises directly from the structure of quantum mechanics itself, when that structure is followed without interruption. Whether or not one finds it convincing is a separate matter. Critics often point out that these other branches are inaccessible. There is no way to communicate with them. No experiment can reach across branches to verify their existence. From an experimental standpoint, they might as well not exist. Supporters reply that this criticism applies equally to many theoretical entities in physics. We accept things we cannot directly observe because they make the theory coherent and predictive. The test is not visibility, but consistency. What makes many worlds especially interesting for our story is how it reframes the measurement problem. Instead of asking why a collapse occurs, it asks why we experience only one branch. The answer lies not in special dynamics, but in perspective. Observers are part of the branching. They do not stand outside it. From within a branch, all alternatives feel as though they vanished. From outside, none of them did. This interpretation also gives a new meaning to probability. If all outcomes occur, what do probabilities represent? In many worlds, probability is not about which outcome will happen, but about how the branches are weighted. Some branches are more prominent, more richly represented in the structure of the probability wave. Observers are more likely to find themselves in those branches. This idea can feel abstract, but it mirrors something familiar. When rolling a die many times, all outcomes are possible, but some appear more frequently. Probability describes typical experience, not absolute exclusion. Still, many worlds remains controversial, not because it fails experimentally, but because it demands a radical shift in how we think about reality. It asks us to trade a single, collapsing universe for a vast, branching one. A universe that never truly chooses, but allows all possibilities to unfold. As you let this idea drift through your thoughts, there is no need to accept it. Many physicists do not. Others find it elegant. Some find it unsettling. Some find it inevitable. What matters for now is not which interpretation is correct, but what they reveal about the nature of the problem. The measurement problem is not a puzzle with an obvious missing piece. It is a crossroads where different values lead to different paths. Simplicity of equations, economy of worlds, comfort of experience. Each interpretation chooses differently. Many worlds chooses the equations, and in doing so, it offers a vision of reality that is vast, quiet, and endlessly unfolding. A place where the universe never stops exploring its own possibilities, even as each observer experiences only a single narrow thread. As your breathing slows, you might notice how this idea echoes something gentle and familiar. In dreams, many storylines can exist at once. Possibilities overlap, scenes shift without explanation. Only when you wake does one narrative remain. Perhaps reality, at its deepest level, is more dreamlike than we usually allow. In the next part of our journey, we will explore a different way of resolving the same tension, a way that keeps one universe, but explains why its possibilities quietly stop interfering with one another. For now, let the image of branching stories fade into the background. You do not need to follow them all. You only need to rest in the one you are in. After wandering through the vast, branching landscape of many worlds, it can feel as though we have travelled very far from the quiet screen where dots slowly formed a pattern. But the journey circles back gently towards something more familiar, toward an explanation that does not multiply universes and yet does not rely on sudden, mysterious collapse either. This explanation is known as decoherence. At first the word sounds technical, even cold, but the idea it describes is surprisingly gentle. Decoherence is not about destroying possibilities, it is about separating them. To see how this works, imagine two voices singing together in a perfectly quiet room. When their tones align, you hear harmony. When they differ, you hear interference, a rich pattern of sound created by overlap. But now imagine opening the windows. Street noise drifts in, air moves, other sounds begin to mingle. The two voices are still singing, but their delicate interaction becomes harder to hear. Eventually, the interference fades, not because the voices stopped, but because the environment grew too loud. In quantum systems, the environment plays a similar role. When a system is carefully isolated, its overlapping possibilities can interfere with one another. This interference is what produces the patterns we have been discussing. But perfect isolation is fragile. The moment a system begins to interact with its surroundings, even in subtle ways, those surroundings start to absorb information. Air molecules bump into particles, light scatters off surfaces, heat flows, vibrations ripple outward. Each interaction leaves a faint imprint of what happened, and as these imprints accumulate, the delicate connections between overlapping possibilities begin to unravel. Not suddenly, not violently, quietly. Decoherence describes this quiet unraveling. From the outside, it can look as though the system has chosen an outcome, but from within the mathematics, nothing special has happened. The probability wave continues to evolve smoothly. What changes is that the different possibilities stop influencing one another. They lose the ability to interfere. They stop talking. Once this happens, the patterns that revealed superposition fade from view. The system begins to behave as though only one outcome exists, even though the underlying structure still contains many. This is why decoherence is often described as explaining the appearance of collapse without invoking collapse itself. The "and" does not disappear, it becomes inaccessible. This idea helps clarify why quantum weirdness is so hard to observe in everyday life. Large objects are never isolated. They are constantly exchanging information with their surroundings. Every collision, every photon, every vibration acts like a tiny measurement, spreading information outward. By the time something reaches a scale we can see or touch, decoherence has already done its work. The overlapping possibilities have been separated so thoroughly that they may as well belong to different worlds, even if no branching is explicitly assumed. This perspective also explains why building quantum technologies is so challenging. Quantum computers, for example, rely on maintaining delicate superpositions and entanglement, but the environment is always waiting. Stray heat, electrical noise, imperfect materials. All of these act like open windows, letting interference fade away. Engineers spend enormous effort trying to keep quantum systems quiet, not silent but sheltered, protected just long enough for calculations to complete before decoherence takes over. In this way, decoherence is not an abstract idea. It is something scientists wrestle with daily in laboratories around the world. It marks the boundary between the quantum and classical behaviors we observe. Another gentle insight decoherence offers is about irreversibility. In principle, if all environmental interactions could be tracked and reversed, interference could be restored. But in practice, this is impossible. The information spreads too far, too fast. It becomes woven into the vast complexity of the environment. Recovering it would require undoing countless interactions, each dependent on the last. The loss of interference is not a fundamental law. It is a practical one, a consequence of complexity. This helps explain why time seems to flow in one direction in our experience. Once information spreads outward, it does not naturally gather itself back together. The past leaves traces, the future does not. Decoherence contributes to this arrow of experience, quietly reinforcing the sense that outcomes once realized are fixed. It is important to notice what decoherence does not do. It does not tell us which outcome occurs. It does not single out a particular result. It does not explain why one branch feels real and others do not. It explains why alternatives stop interfering, not why one becomes our experience. In this sense, decoherence does not solve the measurement problem. It reframes it. It tells us that the transition from "and" to "or" does not require a dramatic physical event. It emerges naturally from interaction with the environment. But it leaves open the deeper question of whether all possibilities continue to exist, or whether something else selects a single outcome. Different interpretations answer that question differently. Decoherence itself remains neutral. This neutrality is part of its appeal. It does not ask us to commit to a particular view of reality. It simply describes a process that must occur if quantum systems are to behave as they do in practice. As you rest with this idea, it may begin to feel less unsettling than earlier interpretations. Decoherence does not expand reality into countless worlds. Nor does it invoke mysterious collapses. It shows how classical behaviour can emerge naturally from quantum rules, given enough interaction and complexity. The world we experience, solid and definite, is not imposed on quantum reality. It grows out of it, layer by layer, as information spreads and interference fades. This view fits comfortably with everyday experience. You do not see overlapping states because the world is too noisy, too connected, too full of interaction to allow them to survive. The quiet required for quantum is rare at human scales. And yet, in carefully controlled conditions, that quiet can still be found. In laboratories, in delicate experiments. In tiny systems briefly sheltered from the world. There, for a moment, possibilities speak together again. As your thoughts slow, you might notice how this mirrors something familiar. When the mind is quiet, thoughts overlap, drift, and mingle. When the day grows busy, they separate into clear tasks and decisions. The environment shapes experience, not by commanding it, but by surrounding it. Decoherence offers a vision of reality that is neither abrupt nor mystical. It is gradual, contextual, gentle. And it prepares us for the final question in this sequence of interpretations. If quantum mechanics predict so accurately, and if decoherence explains so much, is the theory complete? Or is it still a remarkably effective approximation, pointing towards something deeper? That question will guide us into the next session. For now, let the image rest. A quiet system, a noisy world, possibilities slowly drifting apart, not because they are destroyed, but because they can no longer hear one another. After walking through superposition, measurement, interpretation, and decoherence, a quiet question begins to surface. It does not arrive suddenly or demand an answer. It lingers, patient and unresolved, much like the quantum world itself. If quantum mechanics predicts experimental results with extraordinary accuracy, if it guides technology with unwavering reliability, and if its strange features can be lived with in several coherent ways, then what exactly is missing? Is quantum mechanics a complete description of reality, or is it an incredibly precise approximation of something deeper? This question has followed the theory from its earliest days, and it has never fully gone away. To understand why, it helps to separate two ideas that are often blended together. One is predictive success, the other is descriptive completeness. Quantum mechanics excels at the first. Given a setup, it tells us what outcomes to expect and how frequently they will occur. No other physical theory has been tested so thoroughly, across so many different domains, with such consistent success. But predictive power does not automatically guarantee that a theory tells the whole story. A map can guide you through a city with perfect accuracy, while still leaving out details about the texture of the streets, the smell of the air, or the inner lives of the people who live there. It does not lie, it simply focuses on what it was designed to show. Some physicists have suggested that quantum mechanics may be like that map, incredibly useful, remarkably precise, and yet not necessarily complete as a description of what reality is, only of how it behaves when probed. One of the voices often associated with this perspective belongs to a physicist named Gerard 't Hooft. His view is not that quantum mechanics is wrong, but that it may not be the final layer of explanation. According to this line of thinking, the theory could be an effective framework, emerging from deeper rules that we have not yet uncovered. In this view, quantum mechanics is not abandoned. It is respected, but it is not idolized. The idea is subtle. Quantum theory works too well to discard. Any deeper description would have to reproduce its predictions with extraordinary fidelity. The familiar probability patterns, the interference effects, the statistical regularities, all of them would still appear. but they might arise from a structure that looks very different when viewed from below. This possibility appeals to a long tradition in physics. Many successful theories have turned out to be approximations. Newton's laws work beautifully for everyday motion, yet they emerge from a deeper framework of relativity. Classical thermodynamics describes heat and energy with elegance, yet it emerges from the collective behaviour of countless particles. In each case, the older theory was not wrong, it was incomplete. The suggestion that quantum mechanics might one day take its place in this lineage is both exciting and unsettling. It implies that the strangeness we currently accept may not be fundamental, that the and of superposition, the appearance of randomness, and the mystery of measurement might arise from rules that are, at some deeper level, deterministic. But this idea comes with challenges. Any deeper theory would need to explain why attempts to reveal hidden variables have failed, why experiments that test for predetermined outcomes consistently align with quantum predictions instead, why entanglement produces correlations that resist classical explanation. Some approaches propose that the underlying structure may be non-local, or that it operates in a way that does not fit neatly into our usual notion of cause and effect. Others suggest that information itself may be more fundamental than particles or fields. What unites these ideas is a shared humility, a recognition that even our most successful theories may be provisional. At the same time, many physicists argue that quantum mechanics may already be complete in the only sense that matters. It may not describe an underlying mechanism because there is no deeper mechanism to describe. The probability wave, the superposition, the emergence of outcomes may not be signs of missing pieces, but features of reality itself. From this perspective, asking for more may be like asking what lies north of the North Pole. The question assumes a structure that does not exist. This debate is not one that experiments can currently resolve. Both sides agree on what will happen when measurements are made. The disagreement lies in how those outcomes should be understood, and that is an important distinction. Physics, at its core, is an empirical science. Its authority comes from what can be tested. Questions about completeness often drift into philosophical territory, where intuition and preference play a larger role. Some minds are drawn to underlying order, others are comfortable with fundamental uncertainty. Neither stance is irrational. What is remarkable is that quantum mechanics accommodates both. It allows us to calculate with confidence, even while disagreeing about what those calculations ultimately represent. Few theories have been so productive while remaining so open to interpretation. As you rest with this idea, it may help to notice how this openness mirrors the subject itself. The quantum world does not rush to close its stories. It leaves room for multiple perspectives, each consistent with the same facts. This openness has not slowed progress. If anything, it has encouraged creativity. Different interpretations have inspired new questions, new experiments, and new connections between fields. Ideas about information, entanglement, and emergence have grown directly from the discomfort with completeness. In recent years, this discomfort has led physicists to explore connections between quantum theory, gravity, and the structure of space and time. In these explorations, quantum mechanics is not discarded, but woven into a larger tapestry, one where space-time itself may not be fundamental, but something that emerges from deeper relationships. Whether these efforts will lead to a new theory, or simply deepen our appreciation of the existing one, remains an open question. For now, quantum mechanics stands as a theory that is both finished and unfinished, complete enough to describe the world with astonishing accuracy, incomplete enough to invite further exploration. There is something quietly beautiful about that balance. As your thoughts slow and the weight of the day eases, it may feel comforting to know that even in physics, certainty has limits. That understanding is not a destination, but a process, that the universe allows us to know much while still holding something back. In that sense, quantum mechanics may be less like a final answer and more like a conversation that continues across generations. Each experiment adds a sentence, each interpretation offers a tone, and the deeper structure, whatever it may be, remains patiently out of reach. For now, that is enough. The question of completeness does not demand resolution tonight. It can rest, unresolved, just like the possibilities that quietly underlie the certainty of your experience. As we move beyond questions of measurement and completeness, the story of quantum reality begins to stretch outward, not just deeper into theory, but wider across space itself. Up to now, we have been focused on what happens to a single system when it is measured, when possibilities narrow into experience. But there is another phenomenon, just as quiet and just as unsettling, that asks us to rethink what separation even means. This phenomenon is known as entanglement. At first, entanglement does not announce itself as dramatic. There are no explosions, no visible distortions of space. Two particles are created together or interact briefly and then move apart. That is all. And yet something about them remains linked, even as distance grows between them. To understand this link, it helps to release one familiar assumption. The assumption that objects carry their properties independently, like sealed containers moving through space. In the quantum world, properties can belong not to individual objects, but to relationships. Entanglement is not about messages being sent from one particle to another. Nothing travels between them. No signal crosses the distance. Instead, the particles share a single description. Their states are defined together as parts of a whole, even when they are far apart. A gentle way to picture this is through a pair of gloves placed into two boxes. If you open one box and find a left glove, you immediately know the other box contains the right one. But this analogy only goes so far, because in the quantum case, the gloves are not assigned in advance. Before either box is opened, the gloves are not left or right. The description remains open. Only when one is checked does the relationship settle into a definite form. This is where entanglement begins to feel strange. The outcome on one side seems to be tied instantly to the outcome on the other, no matter how far apart they are. Distance, which usually softens influence, appears irrelevant. Einstein famously disliked this implication. He referred to it as a kind of spooky action at a distance, not because it involved ghosts, but because it violated his sense of how causation should work. Nothing, he believed, should influence something else faster than light. Entanglement challenges that belief, but in a subtle way. There is no faster-than-light communication. You cannot use entanglement to send messages. The correlations only become apparent when results from both sides are compared later. What is violated is not causality, but a deeper intuition about separateness. In an entangled system, the parts are not fully independent, even when they are spatially separated. The system behaves as a single entity spread across space. This idea grows clearer when we look at specific experiments. Pairs of particles are prepared so that certain properties are linked. When one particle is measured, the outcome appears random. There is no way to predict it in advance. But when the results from both particles are brought together, a striking pattern emerges. The correlations are stronger than any explanation based on pre-assigned values would allow. It is as if the universe is coordinating outcomes, not by communication, but by structure. What makes this even more remarkable is that these correlations persist across enormous distances. Experiments have confirmed them with particles separated by kilometers, even when measurements are made so quickly that no light-speed signal could connect the events in time. The universe behaves as though distance is not the fundamental barrier we once imagined. This does not mean that space is irrelevant. It means that space may not be the whole story. Entanglement suggests that there is a layer of reality beneath space, a layer where relationships matter more than location. Two particles can be close in this relational sense, even when they are far apart in physical distance. This idea can feel abstract, so it helps to ground it in something familiar. Think about a conversation shared between two people who once lived together. Years later, separated by continents, they can still finish each other's sentences. Not because they are sending signals faster than sound, but because they share a history. A structure of understanding built earlier that still shapes how they respond. Entangled particles share something like that history. A common origin or interaction that binds their descriptions together. Measurement reveals that shared structure, rather than creating it. Another important point is that entanglement is not rare. It is not a fragile curiosity. In the quantum world, it is everywhere. Any interaction that links systems together can produce entanglement. In many body systems, it becomes the rule rather than the exception. This ubiquity has led physicists to rethink what entanglement represents. Instead of treating it as an oddity, some now see it as a fundamental resource, a kind of glue that holds quantum reality together. Entanglement also reframes our understanding of information. Information is no longer something that belongs to individual objects alone. It can be distributed across relationships. The whole can contain information that no part carries by itself. This realization has practical consequences. It underlies quantum computing, quantum cryptography, and other emerging technologies. But its deeper implication is philosophical. It suggests that the universe may be less like a collection of things and more like a web of connections. As you sit with this idea, notice how gently it reshapes familiar concepts. Separation becomes relative. Independence becomes contextual. The notion of an isolated object begins to fade. And this fading prepares us for an even deeper turn in the story. If entanglement links particles across space, could it also be linked to space itself? Could the structure of space-time emerge from patterns of entanglement, rather than existing as a fixed stage on which events unfold? This question might sound speculative, but it arises naturally from trying to reconcile quantum theory with gravity. In the next sessions, we'll see how black holes, holography, and even the idea of wormholes bring entanglement into direct conversation with the fabric of space and time. For now, let the image remain simple. Two particles far apart yet described together. A universe that allows connection without communication. A reality where distance does not erase relationship. As your breathing slows and your thoughts drift, you may find something unexpectedly comforting in this. The idea that separation is not always final, that at a deeper level, things can remain linked even as they move apart. Quantum reality, it seems, is not built from lonely points scattered through space, but from quiet threads of connection, woven together into a whole that is richer than any single part. And with that gentle image in mind, we are ready to continue outward, toward the places where these threads begin to shape the very geometry of the universe. Once entanglement enters the story, it brings with it an uncomfortable tension. On one hand, experiments suggest that distant particles behave as a single, coordinated system. On the other hand, everything we have learned from everyday experience insists that objects carry their own properties, independent of what happens elsewhere. For many years, physicists hoped that this tension could be resolved quietly, without abandoning the familiar structure of reality. Albert Einstein was among them. Einstein did not deny the success of quantum mechanics. He helped build its foundations. but he was deeply uneasy with what entanglement seemed to imply. He believed that the universe should be local, meaning that events in one place should not instantly affect events far away. And he believed that physical properties should exist before they are measured, not appear only when we look. To preserve these ideas, Einstein and his collaborators suggested that quantum mechanics might be incomplete. Perhaps particles carry hidden instructions, values that determine the outcome of any measurement in advance. The apparent randomness would then reflect our ignorance, not a fundamental feature of nature. This proposal felt reasonable. It matched centuries of physical intuition. It allowed reality to remain orderly, even if our knowledge was limited. For a long time, this possibility remained open. Then, in the middle of the 20th century, a physicist named John Bell asked a simple but powerful question. If the universe really works this way, with pre-existing properties and local influences, what patterns should we see in experiments? Bell did not propose a new interpretation, he derived a test. In gentle terms, Bell showed that any theory based on local hidden instructions must obey certain statistical limits. There are ceilings on how strongly distant outcomes can be correlated if those outcomes are decided independently and influenced only by nearby events. Quantum mechanics, however, predicts correlations that exceed those limits. This difference is not subtle. It is not a matter of interpretation. It is a clear numerical distinction between two kinds of worlds. One world respects classical intuitions about locality and pre-existing properties. The other does not. Bell's work transformed a philosophical debate into an experimental question. Over the following decades, increasingly refined experiments were performed. Pairs of entangled particles were created and sent to distant detectors. Measurements were chosen quickly and randomly, leaving no time for communication at the speed of light. The results were recorded independently and compared afterward. Again and again, the outcome was the same. The correlations observed in nature exceeded the classical limits. They matched the predictions of quantum mechanics with remarkable precision. The universe, it seemed, had made a choice. This does not mean that information travels faster than light. No message is sent. No signal crosses the distance. What fails is the idea that outcomes are fixed in advance and merely revealed by measurement. Instead, the correlations appear to be woven into the structure of reality itself. The outcomes are not independent facts waiting to be uncovered. They are joint events, emerging together from a shared quantum description. This realization can feel deeply unsettling because it forces us to reconsider what we mean by explanation. We're used to explaining things by breaking them into parts, assigning properties to each part, and tracking how those properties influence one another. Entanglement resists this approach. In entangled systems, the whole is more than the sum of its parts. The most complete description belongs to the pair together, not to either particle alone. Bell's theorem does not tell us which interpretation of quantum mechanics is correct. It does not choose between collapse, many worlds, or other frameworks. What it does is narrow the field of acceptable stories. Any story that preserves both strict locality and pre-existing properties cannot describe our universe. Something has to give. Different interpretations respond differently. Some relax locality. Others relax the idea of independent properties. Some accept a deeper level of structure that does not fit neatly into space and time as we usually understand them. What unites these responses is a shared recognition that classical comfort has limits. This does not mean that everyday reality is an illusion. Tables remain solid, clocks tick reliably, signals obey the speed of light. But beneath these familiar behaviors lies a deeper layer where connections are not constrained by distance in the way we expect. This deeper layer rarely intrudes into daily life because its effects average out. Decoherence hides it. Complexity overwhelms it. but in carefully designed experiments, its signature becomes undeniable. There is something quietly profound about this. The universe does not behave like a machine assembled from independent parts. It behaves more like a tapestry, where threads carry meaning only in relation to one another. As you let this idea settle, it may help to notice how gently the shift occurs. Nothing dramatic happens in these experiments. No flashes of light streak across the sky. No alarm sound. The evidence accumulates through careful statistics, repeated trials, and patient analysis. Reality reveals itself not through spectacle, but through consistency. Bell's work marks a turning point in our understanding. It shows that the strangeness of quantum mechanics is not a matter of interpretation alone. It is written into the fabric of experimental results. Any attempt to restore a purely classical picture runs into a wall of data. And yet, this is not a reason for despair. It is an invitation. An invitation to expand our sense of what explanation can mean. To accept that some connections may be more fundamental than distance, that some properties may exist only in relation to others, that reality, at its deepest level, may be less about objects and more about structure. As your thoughts slow, you might find this idea less disturbing than it first appears. The world does not become chaotic when classical assumptions fail. It becomes richer, more subtle, more interconnected. In the quiet of these experiments, we glimpse a universe that refuses to be carved cleanly into separate pieces. A universe that asks us to think in terms of wholes, patterns, and relationships. And this glimpse prepares us for the next stage of the journey. If entanglement reveals connections that transcend distance, and if these connections are fundamental, then it is natural to ask whether they play a role in shaping space itself. Could the geometry of the universe emerge from the same quantum relationships that link particles together? To explore that possibility, we must turn toward one of the most extreme environments known to physics, a place where gravity, quantum theory, and information collide. For now, let the image linger. Two distant particles, measurements made, results compared, and a quiet realization settling in. The universe is not built from independent facts scattered across space. It is built from correlations, woven together in ways that challenge our deepest intuitions, yet remain perfectly consistent with everything we observe. There are moments in science when a problem is so unsettling that it forces an entire field to stop and listen. Not because the math fails, but because the implications feel impossible to accept. The story of black holes and information is one of those moments. For a long time, black holes were thought of as cosmic endings, regions of space where gravity becomes so strong that nothing escapes, not light, not matter, not even time in any familiar sense. Once something crossed the boundary of a black hole, it was gone forever, sealed behind a horizon from which no return was possible. At first, this seemed dramatic but manageable. After all, classical physics is comfortable with loss. Energy can dissipate, motion can fade, heat can spread until it is no longer useful. Perhaps black holes were simply the universe's way of cleaning up loose ends. Then quantum theory entered the picture. In the 1970s, physicist Stephen Hawking made a discovery that changed how black holes were understood. When quantum effects are taken into account, black holes are not perfectly black. They glow very faintly with what is now called Hawking radiation. This radiation is not explosive or violent. It is a slow, quiet leak of energy, like warmth seeping from a cooling ember. Over unimaginably long times, this gentle leaking causes black holes to shrink, and eventually, if left undisturbed, they evaporate completely. At first glance, this sounds almost poetic. Even the darkest objects in the universe are temporary. Nothing lasts forever. But hidden inside this idea was a profound problem. If a black hole forms from ordinary matter and then slowly evaporates into a faint haze of radiation, what happens to the information about what fell in? The details of the particles, their arrangements, their histories. In quantum mechanics, information is not a casual detail, it is sacred. The theory is built on the idea that information is never truly destroyed, only transformed. Hawking's original calculation suggested that the radiation emitted by a black hole carries no memory of what went in. It looks random, thermal, featureless. If that were true, then information would be lost forever when the black hole disappears. This was not just a technical issue, it was a crisis. If information can be truly destroyed, then quantum mechanics, as we understand it, breaks. The careful accounting of probabilities fails, predictability dissolves, the past no longer constrains the future, physics loses its grip on consistency. This is why the information paradox was never treated as a curiosity. It struck at the foundation of the theory itself. Physicists found themselves facing an uncomfortable choice. Either accept that quantum mechanics fails in the presence of black holes, or find a way for information to survive, even when everything else seems to vanish. Most chose the second option, not because it was easier, but because the alternative was too costly. Quantum mechanics had proven itself too reliable, too deeply woven into every successful description of nature, to abandon lightly. If something had to give, it would have to be our understanding of black holes, not the core principles of quantum theory. And so began a long, quiet effort to understand how information might escape a black hole without violating everything we know about gravity and causality. One possibility was that information somehow leaks out with the radiation, encoded in subtle correlations too fine to notice at first. Another was that information remains stored at the boundary of the black hole, the horizon itself, rather than falling into an unreachable interior. This shift in thinking marked a profound change. The event horizon, once imagined as a simple boundary, began to look like an active participant, not just a line in space, but a surface that remembers. The idea that a surface could store information about a volume feels counterintuitive. We are used to thinking that the inside of something holds its content, but black holes suggested the opposite, that the information describing everything that fell in might be encoded on the outer boundary, spread thinly across it like an intricate pattern. This was not a metaphor chosen for convenience. It arose from careful reasoning about how much information can be packed into a region of space without forming a black hole. Again and again, calculations pointed to the same conclusion. There is a limit, and that limit depends not on the volume, but on the surface area. This was the first hint of something extraordinary. If the maximum information in a region is proportional to its surface, then space itself may not be the fundamental container we imagine. The interior may be, in some sense, a projection of what is written on the boundary. At this stage, the story shifts from crisis to possibility. The information paradox forced physicists to confront the idea that space and time might not be basic ingredients of reality, that they might emerge from something deeper, something more abstract, like information and its relationships. Black holes, once seen as cosmic dead ends, became laboratories for testing the limits of understanding. Places where gravity, quantum mechanics, and information theory are forced into the same conversation. What makes this especially striking is how gently the universe presents the problem. Black holes do not announce the paradox with drama. They sit quietly, leaking energy over timescales far longer than the age of the universe. The crisis exists not in observation, but in interpretation. And yet, this quiet tension reshaped theoretical physics for decades. The information paradox pushed researchers to explore new ideas about entropy, geometry, and the nature of space itself, it suggested that information is not a secondary feature of reality, but a central one. Perhaps the most central of all, as you let this idea rest, notice how it echoes themes we have already encountered: the shift from objects to relationships, from definite things to patterns of possibility, from space as a stage to space as something that might arise from deeper rules. Black holes did not introduce these ideas out of nowhere. They sharpened them. They made it impossible to ignore the question of what reality is really built from. And they prepared the ground for a remarkable proposal that would follow. A proposal suggesting that the universe, at its most fundamental level, might behave less like a solid structure and more like a kind of projection. A world where the deepest description lives not in the volume of space, but on its boundaries. That proposal will guide us into the next part of the journey. For now, let the image remain simple: a black hole slowly fading, information that refuses to disappear, and a universe that quietly insists on consistency, even when it challenges our most basic intuitions. In the darkness of space, nothing is truly forgotten. The past leaves its traces not always where we expect, but always somewhere. And with that thought settling gently, we can move forward toward the strange idea that the surface of the universe may remember everything the inside ever was. Once the information paradox was taken seriously, physics found itself standing at the edge of a remarkable possibility. The question was no longer only whether information survives black holes, but whether information lives, and what that might mean for the structure of reality itself. The answer that slowly emerged was not intuitive. It did not match how we naturally picture space. And yet, again and again, different lines of reasoning pointed toward the same quiet suggestion. Information may belong to surfaces, not volumes. To appreciate how strange this is, it helps to begin with something familiar. Imagine a book. The story lives in its pages. If you want to know what is inside the book, you open it and read the interior. The cover, by contrast, tells you very little. We are deeply accustomed to the idea that contents are stored inside containers. Black holes seem to challenge that habit. Careful reasoning about gravity and quantum theory revealed a surprising limit. There is a maximum amount of information that can be stored in a region of space before it collapses into a black hole. And that maximum does not depend on how much space is inside the region. It depends on the size of its boundary. The larger the surface, the more information it can hold. The interior volume, strangely, does not matter. This insight was not discovered in a single leap. It appeared gradually across different calculations, each pointing to the same conclusion. The universe seems to enforce an upper bound on information density, and that bound is written on surfaces. From this realization grew what is now called the holographic principle. The name is evocative, but the idea is subtle. A hologram is an image that appears three-dimensional, even though all the information needed to produce it is encoded on a two-dimensional surface. The depth we perceive is not stored inside the image. It emerges from how the surface information is organized. The holographic principle suggests that the universe may work in a similar way. Everything that appears to exist within a region of space could be fully described by information encoded on its boundary. The three-dimensional world we experience might emerge from a deeper, lower-dimensional description. This does not mean the universe is an illusion. It means that our intuitive picture of where information lives may be incomplete. To soften this idea, imagine watching a movie projected onto a screen. The screen itself is flat. The story appears rich, deep, and immersive. Characters move through landscapes. Events unfold in time. But all of that complexity is encoded on a thin surface translated into light. The holographic hints suggest that space itself might be like that movie. What we experience as volume, distance, and depth could emerge from patterns of information written elsewhere. This idea gained strength from unexpected connections between different areas of physics. In certain simplified models of the universe, physicists discovered exact mathematical relationships between a theory describing gravity in a volume and a theory describing quantum interactions on a boundary. These were not approximations or metaphors. They were precise correspondences, two very different descriptions, yet perfectly matched in their predictions. Once again, we can leave the technical details aside and focus on the message. Gravity and space-time inside a region can be fully captured by quantum information living on its surface. This was not just a clever trick. It offered a powerful way to think about black holes. If information is stored on the horizon, then nothing is truly lost when a black hole evaporates. The information remains encoded on the surface and can, in principle, be recovered. The paradox softens, but the implications go much further. If space-time emerges from surface information in these models, then space is not fundamental. It is a derived concept, a convenient way of organizing deeper relationships. The geometry we move through every day could be the large-scale expression of underlying patterns of information. This idea fits remarkably well with themes we've already encountered. Quantum mechanics emphasizes relationships over objects. Entanglement distributes information across systems. Decoherence explains how classical behavior emerges from quantum interactions. Holography adds another layer, suggesting that space itself may be a kind of emergent bookkeeping. What is especially striking is how these ideas converge from different directions. Black hole physics, quantum information theory, and studies of space-time geometry all point toward the same conclusion. Information is not just something that moves through space. It may be what space is made of. At this point, it is important to remain gentle and cautious. The holographic principle is not a proven fact about our universe. It is a powerful idea supported by strong evidence in certain contexts. Whether it applies universally remains an open question. But even as a hint, it reshapes how physicists think. It suggests that the deepest description of reality may not involve distances, directions, or even time in the way we experience them. Those features may emerge only when information is organized in particular ways. As you sit with this idea, notice how it reframes earlier puzzles. The non-local connections of entanglement become less mysterious if space itself is secondary. The strange behavior of black holes becomes less threatening if horizons are active repositories of information. The difficulty of unifying gravity and quantum mechanics begins to look less like a clash of theories and more like a mismatch of perspectives. We have been trying to combine two descriptions that operate at different levels. Holography hints at a common foundation beneath both. This does not mean the universe is simple. On the contrary, it suggests a richness that goes beyond our usual categories. Reality may be layered. What feels fundamental at one scale may be emergent at another. As your thoughts drift, it may help to think of space as a language rather than a substance. A way the universe organizes experience, not the raw material from which everything is built. This language is extraordinarily effective. It allows planets to orbit, light to travel, and lives to unfold. But like any language, it may be a translation of something deeper. The holographic hint invites us to imagine that deeper level, a place where information and relationships come first, and where space appears only when those relationships are arranged in certain patterns. In the next part of our journey, we will explore an idea that takes this hint one step further. If space emerges from information, and if entanglement links distant regions, then perhaps entanglement itself is what gives space its shape. For now, let the image rest gently. A flat surface, a rich world unfolding from it, depth emerging without being stored inside. Reality, it seems, may be less like a solid container and more like a story projected from a deeper script, and as that thought settles, we can continue forward toward the idea that the geometry of the universe may be woven from the same quiet threads that link quantum systems together. By the time physicists began taking the holographic idea seriously, something curious had already happened. The conversation about entanglement had quietly shifted. It was no longer being treated as a strange side effect of quantum theory, nor merely as a resource for future technologies. Instead, entanglement began to look like something far more fundamental. It began to look like structure. Up to this point, we have spoken of entanglement as a link between distant particles, a shared description that survives separation. But if space itself may not be fundamental, then the role of entanglement must be reconsidered. It may not just connect things within space, it may help create space in the first place. This is a subtle but profound shift. Rather than imagining space as a stage on which quantum systems interact, this perspective suggests that space emerges from the pattern of interactions themselves. Entanglement becomes the quiet scaffolding from which geometry is built. To approach this idea gently, imagine a fabric woven from threads. The strength and shape of the fabric depend not on the threads alone, but on how tightly they are woven together. If the threads are loosely connected, the fabric is weak. If the connections are cut, the fabric tears. In modern theoretical physics, entanglement plays a role similar to those threads. Studies of simplified universes, often using holographic models, have revealed a striking pattern. Regions of space that are strongly entangled behave as though they are close together geometrically. Regions with little or no entanglement behave as though they are far apart, or even disconnected. Distance, in this view, is not a primitive concept. It is reflection of how much information is shared. This idea leads to a powerful and unsettling thought experiment. What happens if entanglement is gradually reduced between two regions of space? According to these models, the geometry between them begins to stretch. The connection weakens. If entanglement is removed entirely, the space can effectively tear apart. Space does not merely host relationships, it depends on them. This perspective helps reframe the strange non-local behavior we encountered earlier. If entanglement is woven into the fabric of space itself, then correlations that seem to ignore distance are not violations of locality. They are expressions of a deeper connectivity that underlies distance. One of the most evocative images to emerge from this line of thinking involves wormholes. Traditionally, wormholes are imagined as tunnels through spacetime, shortcuts connecting distant regions. In science fiction, they are dramatic and unstable. In physics, they are delicate mathematical solutions that usually collapse before anything can pass through. But in recent theoretical work, wormholes appear in a new role, not as travel routes but as geometric expressions of entanglement. The idea is not that entangled particles are connected by literal tunnels you could fly through. Instead, the mathematics describing entanglement between two systems can be mapped onto the mathematics describing a wormhole-like connection between regions of space. The wormhole becomes a picture, a way of drawing entanglement in geometric language. In this picture, strong entanglement corresponds to a smooth, connected geometry. Weak entanglement corresponds to stretched, fragile connections. No entanglement corresponds to separation. Once again, the emphasis is not on spectacle, but on structure. What makes this especially compelling is how it ties together many threads we've already followed. The information stored on boundaries, the idea that space emerges rather than exists fundamentally, the role of entanglement in shaping behavior across distance. All of these ideas converge on the same suggestion: reality may be woven from relationships. This does not mean that space is an illusion, or that it can be dismissed. The geometry we experience is real and reliable. It governs motion, energy, and time. But it may be an emergent reality, arising from patterns of quantum information that operate beneath our everyday awareness. In this sense, entanglement becomes more than a feature of quantum systems. It becomes a kind of glue, the quiet binding agent that holds the universe together at its deepest level. This perspective also sheds new light on gravity. Gravity has long resisted unification with quantum mechanics, but if space-time geometry itself emerges from entanglement, then gravity may not need to be quantized in the usual way. It may arise naturally from how entanglement is distributed and how it responds to changes. This idea remains speculative. It is not yet a complete theory. But it has generated a remarkable amount of progress. Calculations that once seemed unrelated now fall into place. Puzzles that once felt isolated begin to echo one another. Even more importantly, this approach shifts the tone of inquiry. Instead of asking how particles move through space, physicists ask how patterns of information give rise to space. Instead of treating geometry as fixed, they treat it as dynamic, shaped by relationships. As you let this idea settle, notice how it changes the emotional texture of the universe. Space becomes less like an empty expanse and more like a living structure. Not alive in a biological sense, but responsive, sensitive to how things are connected. This view also resonates quietly with human experience. Relationships shape our sense of closeness more than physical distance ever could. Two people can be far apart and still feel near. Others can sit side by side and remain distant. At a deep level, connection defines structure. Quantum reality, it seems, follows a similar logic. As your thoughts slow, allow the image to remain gentle. A universe woven from invisible threads. Geometry arising from shared information, distance emerging from patterns of connection. We've travelled far from the double-slit experiment, and yet the thread remains unbroken. The same superpositions and correlations that puzzled early physicists now appear as foundational elements of space-time itself. In the final session, we will return from these deep abstractions to something tangible. A place where superposition and entanglement are not just ideas, but working tools, where the "and" of quantum reality is harnessed, briefly and delicately in the human world. For now, let the universe remain woven, not assembled, connected, not merely arranged, and let that quiet image carry us gently forward. After drifting through paradoxes, horizons, and the quiet suggestion that space itself may be woven from information, it is grounding to return to something tangible, something built by human hands, something that does not merely hint at quantum reality but uses it. This is where quantum computing enters the story. At first, the phrase may sound technical, even cold. Rows of machines, cryogenic chambers, complex circuitry. But beneath that machinery lies a simple and almost poetic idea. The same "and" that puzzled us in the double-slit experiment is not just a theoretical curiosity. It can be made to work. In ordinary computers, information is stored in bits. Each bit is either 0 or 1, off or on. This clarity is comforting. It mirrors the way we experience the world, with definite states and clear distinctions. Classical computation thrives on this certainty. Quantum computers begin from a different place. Their basic units of information, called qubits, do not have to choose between 0 and 1 right away. Instead, they can exist in a gentle overlap of both, not confused, not undecided, simply holding multiple possibilities at once. This overlap is the lived version of superposition. To keep this idea soft, Imagine a musical chord rather than a single note. The chord is not switching rapidly between notes, it contains them together. Only when you isolate one tone do you force a choice. A qubit behaves in a similar way. Until it is measured, it carries a blend of possibilities, and when multiple qubits are entangled, those possibilities become coordinated across the system. This coordination is what gives quantum computers their unique potential. Rather than checking one possibility at a time, a quantum computer explores many related possibilities together. It is not that it tries every answer in parallel like a collection of tiny classical machines. Instead, it allows interference between possibilities to amplify useful patterns and suppress unhelpful ones. Once again, the mathematics is precise, but the intuition can remain gentle. Quantum computation is about shaping the landscape of possibilities so that the right answers stand out when a measurement is finally made. What makes this remarkable is not just that it works in principle, but that it works in practice. Real quantum computers exist. They are fragile, imperfect, limited, but they operate. They maintain superposition and entanglement long enough to perform meaningful tasks. They demonstrate again and again that the "and" of quantum reality is not an illusion. It is something that can be engineered, however delicately. This brings us back to a familiar figure in our story: decoherence. Decoherence is the ever-present challenge facing quantum technologies. The environment, with its noise and complexity, constantly threatens to disrupt superposition. Heat, vibration, stray electromagnetic fields, even tiny imperfections in materials can cause qubits to lose their quantum character. When this happens, the "and" collapses into an "or," not through a dramatic measurement, but through gradual entanglement with the environment. The system becomes classical. The magic fades. In this way, quantum computers sit at a boundary. They are not fully quantum worlds, sealed off from reality, nor are they fully classical machines. They exist in a narrow, carefully maintained middle ground. This fragility is not a flaw, it is a lesson. It reminds us that the quantum world is not hidden because it is unreal, but because it is delicate. The classical world we experience is robust because it is saturated with interaction. Quantum coherence survives only where isolation and control are carefully preserved. Seen this way, quantum computing becomes more than a technological project. It becomes an experiment in understanding reality. Each successful operation is a small victory against noise. Each preserved superposition is a brief window into a deeper layer of the universe. What is especially striking is how this practical achievement loops back to the philosophical questions we began with. The measurement problem, the role of observation, the transition from "and" to "or." In a quantum computer, these questions are not abstract. They are engineering constraints. Designers must decide when to protect superposition and when to allow measurement. They must choreograph the moment when possibilities are allowed to interfere and the moment when an answer is extracted. Reality here is not passively observed, it is actively shaped. This does not mean humans control quantum reality. It means that by understanding its rules, we can briefly align ourselves with its deeper structure. We can build devices that resonate with how the universe behaves, rather than forcing it into classical molds. As your thoughts slow, it may be comforting to recognize how modest this achievement really is. Quantum computers do not overturn reality. They do not reveal hidden messages or secret dimensions. They simply confirm, quietly and repeatedly, that the strange features we have been discussing are real. Superposition is real. Entanglement is real. Decoherence is real. The "and" exists, even if it rarely survives long in the noisy world we inhabit. And this brings us gently to the end of our journey. We began with particles passing through slits, leaving patterns that defied common sense. We followed those patterns through questions of measurement, interpretation, and completeness. We saw how entanglement challenges separation, how black holes threaten information, how surfaces may encode volumes, and how space itself may emerge from relationships. Along the way, reality became less solid and more process-like. Not a collection of fixed objects, but an unfolding of possibilities. Not a rigid structure, but a dynamic interplay of information, interaction, and emergence. Quantum computing does not resolve these mysteries. It does something quieter. It shows that living with them is possible, that even without final answers we can work, build, and explore. Reality, it seems, does not demand that we fully understand it before engaging with it. As you rest now, let the final image be a gentle one, a system holding possibilities together just long enough for something meaningful to emerge, a universe that allows and before insisting on awe, a reality that is not brittle, but patient. And so we arrive at the end of this exploration. Whether your eyes are still open or your thoughts are already drifting elsewhere, thank you for being part of this quiet journey. If you find comfort in these gentle wanderings through science and wonder, you are always welcome to return. Knowledge does not have to be loud to be profound. Sometimes it is enough to let it unfold softly, like a thought fading into sleep. And with that, wherever you are and however your day has been, may the universe feel a little less strange and a little more kind.